I spent my weekend writing a compression engine that shrinks a transformer's KV cache 5 times, and the model doesn't even notice. This is Qwen 2.5 generating live from compressed memory right now. It's built on 5 custom GPU kernels, all running on NVIDIA's most advanced chip, the Blackwell B200.
This is TurboQuant, a paper Google published at ICLR 2026 literally last week. It tackles what I think is the single biggest bottleneck in LLM inference right now, the KV cache. Every time a large language model generates a token, it caches a key and value vector for that token across every single layer, and that cache grows linearly. So at 8,000 tokens on a 3 billion parameter model, you're looking at almost 300 megabytes of KV cache alone. TurboQuant solves both problems at once. It compresses the KV cache down to just 3 bits per coordinate, so you're storing 1/5 of your data and loading it 5 times faster.
So I took the algorithm, wrote a set of cuTile kernels for Blackwell, and ran it on a real transformer, Qwen 2.5 on a B200. Here's what happened. We take the full KV cache, so 28 layers, every key and value vector, and compress it down to 256 kilobytes. When we let the model run, the results speak for themselves.
The compression is invisible to the model.
And the attention quality is solid. Compared with the PyTorch reference, it's 0.99 cosine similarity across the board. The model is excellent at needle and hay retrieval and scales with long context very well. The trade-off here is the latency. Since we're doing more operations that involve compression and decompression, our kernels take longer to process. To compress a vector, we do something called quantization. Similar to rounding down, you round each coordinate down to the nearest bin. The problem is, raw vectors have outliers, which can stretch your bins disproportionately. TurboQuant fixes this with a random orthogonal rotation that spreads energy evenly across all dimensions without changing the vector's geometry.
And that's when LloydMax comes into the picture. It places 8 centroids along the bell curve, more where the data is dense and fewer at the tails. We literally store 3 bits per coordinate, and that makes sense because you can only create numbers from 0 to 8 using 3 bits. But here's the catch. When you try to reconstruct those vectors from 3-bit indices, there's a small reconstruction loss, which shrinks the vectors towards 0. That means every attention score ends up a little too small. And because softmax exponentiates those scores, even a small bias gets amplified into a completely warped attention distribution. TurboQuant fixes this with something called QJL. You take the quantization error, or what we call the residual, project it through a random matrix, and keep just the sign of each coordinate, positive or negative. That's 1 bit per dimension. At decode time, you use these stored signs to compute a correction term that cancels out the bias. And that's literally it. That's our algorithm. Now, let's go look at the kernels. Okay, so I wrote 5 cuTile kernels that cover the full pipeline, including key and value compression, decompression, attention scoring, and fused attention. But the one I want to walk you through is the fused attention kernel because that's where things get interesting. So each thread block owns a single query tile. It loads Q once into on-chip memory and then streams through every KV block in sequence. For each block, the TMA on the Blackwell pulls data into shared memory and it flows it through TMEM to the tensor cores in a single hop. This is a feature that's unique to Blackwell. The kernel runs 2 matrix multiplies, one for the bulk attention scores and one for the QJL correction. Those get combined into an online softmax, the weighted values accumulate, and in the end, you have your output. It's one kernel that does one pass, and there's no round trips to global memory. Okay, so after profiling and iterating, I added blocks was linked to spread L2 pressure, I pipelined loads with latency hints, and I switched to EXP2 with flush to 0 on the Blackwell fastpath. If you're curious about these optimizations and want to see the performance numbers, I've documented everything in the repo. Cool. So before we end off, I just want to give a quick shout out to Bryce Adelstein-Lelbach and the cuTile team at NVIDIA for lending me access to the Blackwell GPUs for this project. Working with cuTile on this hardware genuinely feels like the future of how we'll be writing GPU kernels, so I'm glad to be a part of it. If you want to dig into the full benchmarks, see the roofline analysis, or all of the optimizations, it's all in the repo. Star it, fork it, rip it apart. I'm just getting started. Thanks.